Good afternoon, class. We are looking at exam 4 review, chapter 4, application of differentiation, chapter 5, integrals, and 6.1 areas between curves. Here's part 3, 5.2, the definite integral, 5.3, the fundamental theorem of calculus, short FTC. 5.2, the definite integral. Suppose a continuous function f is defined on the closed interval of a2. The interval is divided into n subintervals, where delta x is b minus a over a, and x sub 0 is a, x sub 1 is a plus delta x sub 2 is a plus 2 delta x, all the way to x sub n, which is b or a plus n delta x. Then a Riemann sum associated with f is the following sum. The integral of a to b f of x dx is the limit as n goes to infinity of summation of I going from 1 to n, f of x sub I delta x. If we expand that, we get the limit as n goes to infinity of f of x sub 1 delta x all the way to f of x sub n delta x, where again delta x is b minus a over n, and x sub I is a plus I delta x. Let y be equal to f of x be a continuous and non-negative over an interval of a to b. A definite integral is the limit as n goes to infinity equivalently as delta x goes to 0 of the Riemann sum that was discussed, of the area of the rectangles under the graph of y equals f of x over the closed interval of a to b. In other words, the area under the curve is exactly equal to the limit that was mentioned. A equals the limit as n goes to infinity of summation of I going from 1 to n, f of x sub I delta x. Delta x is b minus a over n, x sub I is a plus I delta x. Again, as long as the function is continuous and non-negative. Otherwise, it becomes the difference of areas. Now, 5.3, the definite integral. Let's explain that. Let's see what this is. Integration symbol, the elongated S, integration symbol. The symbol elongated S was introduced by Leibniz and is called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. And so that's the integration symbol. Lower limit of integration is A, upper limit of the integration is B, integrand is f of x. X is considered variable of integration, also known as dummy variable. It is called a dummy variable because the answer does not depend on the variable chosen. The dx simply indicates that the independent variable is x. So the integral of a to b f of x dx is a number. That's why it's called a definite integral. It is a number. It doesn't depend on x. We could use any letter in place of x without changing the value of the integral. The integral of a to b f of t dt gives you exactly the same thing, as long as these two are the same. And of course, the lower and upper limits are a, b. Or it's approximation. The integral of a to b f of x dx is approximated by the Riemann sum, summation I going from 1 to n of f of x sub I delta x, which is f of x sub 1 times delta x plus all the way to the last one, f of x sub n delta x. This sum is called a Riemann sum. The precise value is obtained when we take a limit. Area is the limit as n goes to infinity of summation of I from 1 to n of f of x sub I delta x. Now, this is the way we calculate this. Eventually, we take the easy way out known as FTC, one of the FTCs, fundamental theorem of calculus, capital F of B minus capital F of A, where capital F of X is an antiderivative of lowercase f of x. Expressed as an integral on the interval of 0 to pi. So we have a choice of writing an integral or the limit. And if one is given, we should be able to find the other one, and vice versa. So One format is given. In this case, the limit is given, so we are going to write both of them next to each other. So according to this, the integral of a to b f of x dx is the limit of I going from 1 to n as n goes to infinity of f of x sub I delta x, and the interval is a to b. Okay, well, a and b are given as 0 and pi. What about f of x and f of x sub I is given? This is f of x sub I. This one is f of x sub I. X sub I cubed plus x sub I sine of x sub I. Therefore, f of x must be x cubed plus x sine x. And as far as a and b are concerned, they were given to us right here. So a was given as 0, b was given as pi. And so the integral of a to b f of x dx, we have the function, we have a and b, and we write the given limit, the limit as n goes to infinity of summation of I going from 1 to n x sub I cubed plus x sub I sine of x sub I delta x is the integral of 0 to pi x cubed plus x sine x dx. Now, this is another limit. We want to express it as an integral. The limit as n approaches infinity of summation I going from 1 to n of sine of 2 pi I over n times 2 pi over n. So in essence, I hope you recognize this one when you look at f of x sub I delta x. So this is like delta x. Okay, so let's put them next to each other. First of all, the integral and the limit. Okay, so you compare these two, and you notice this is your function. This is your delta x. A and b are given, everybody. So let's write a is 0, b is 2 pi. That's given. Delta x is, of course, b minus a over n, which makes it 2 pi minus 0 simply 2 pi over n. X sub I is a plus I delta x. So a is 0, delta x is 2 pi over n, then times I. A plus I delta x is 2 pi I over n. So that's exactly. So this is your x sub I, everybody. And so we're going to write f of x sub I is a sine of 2 pi I over n, which makes f of x simply sine x. The interval is given as 0 to 2 pi. So it becomes the integral of a to b. The integral of a to b is 0 to 2 pi. F of x sine x dx. So the limit, the given limit, meaning the limit as n goes to infinity of summation I going from 1 to n of sine of 2 pi I over n 2 times 2 pi over n is the same as the integral of 0 to 2 pi sine x dx. Eventually, this uses the fundamental theorem of calculus for the calculation, but this we will look at shortly, and it's a little bit, complicated. It's not a big deal. So, before we move on, limit versus the integral, we should understand, and we should be able to go from one format to the next. So, for example, we want to use summation formula to compute the integral of 0 to 2 parentheses 1 minus x squared dx. And of course, we know that this is the same as this one. So fundamental theorem of calculus is not discussed yet. We will get to that later on. So how would we find this using the limits? Okay. First, I got to remind you of some of the limit theorems. Summation of the summation theorems. The summation of I going from 1 to n of 1 is n. The summation of I from 1 to n of c is nc. The summation of I going from 1 to n is n times n plus 1 over 2. The summation of I squared I going from 1 to n is n times n plus 1 to n plus 1 over 6. And the summation of I cubed is n squared times n plus 1 quantity squared over 4. So that we should know, so we can use it if need be. So here's what happens. First and foremost, as we look at this one, you should recognize a couple of things. F of x, 1 minus x squared. A to b, 0 to 2. So a is 0, b is 2. So as soon as you see this function, you should recognize this one. Now you do some work. Delta x, b minus a over n, 2 minus 0 over n, or it's 2 over n. X sub I is a, 0, plus I times delta x, 2 over n. So x sub I is 2i over n. Now, when we look at the limit here, we need to calculate f of x sub I given f of x. So how do we come up with f of x sub I? You replace the x with x sub I. So 1 minus x squared for f of x sub I is 1 minus, and you replace x sub I with 2i over n as we discovered that. And so now we are going to go with the limit, and we are going to write just this part. In other words, I'm going to write the summation part and simplify it. When I'm done, then I put it into the limit, okay? I don't have to carry the limit all the way. At the end, I come back to the limit. So I'm going to work on this part, everybody. I'm going to work on this part. So the summation as I goes from 1 to n of f of x of I, this expression times delta x. Delta x is 2 over n. Okay. Now, this times 2 over n is 2 over n. This one is 4i squared over n squared. You multiply by 2 over n. So that becomes 8i squared over n cubed. So we're going to write the summation as I goes from 1 to n. The first piece becomes simply 2 over n, right? The product of these two. And the second piece becomes minus 8i squared over n cubed. To evaluate the sum, we know the summation of 1 is n, and therefore we're going to make this one summation. We take the 2 over n out because remember, this applies to I, and we make this one a second one, and we take minus 8 over n cubed out. So here's what we get. Going from here to here is elementary algebra. So let's pay attention to it one more time. This part, everybody, is this one. Okay. Summation of 2 over n. Summation of 2 over n as I goes from 1 to n. Well, you can take the 2 over n out and you have a 1. Now this part, summation of negative 8i squared over n cubed as I goes from 1 to n, minus, you take 8 over n cubed out and you leave I squared in. Now this one, summation of 1 is n, so replace this with n. This one, replace it with this. So we are going to write 2 over n, summation of 1 is n, minus 8 over n cubed, summation of I squared is n times n plus 1 times 2n plus 1 over 6. Now, because we are going to put this into a limit, everybody, we are going to simplify in the following manner. Of course, these two cancel each other, and this is 2. Please understand that this piece, the first one is 2n cubed. You don't even have to know the rest of them because the denominator is 6n cubed. And the numerator becomes minus 8 times 2, 16n cubed, and a few more. The rest of it, because we want to put it into a limit, Okay, so let me put that into a limit. So this integral of 0 to 2, 1 minus x squared dx is equal to the limit. Now I'm going to apply the limit. As you know, when you want to apply the limit to a rational function, you divide by highest degree term in the denominator. And in short, that drops and the leading coefficients take over. The rest of them, since they have smaller exponent, they all go to 0 as n goes to infinity. So limit as n goes to infinity of 2 minus 16n cubed over 6n cubed plus the rest of them. That would be 2 minus 16n cubed over 6n cubed, which is minus 16 over 6, which is 8/3. And 2 is 6/3. Minus 8/3. Negative 2/3 is the final answer. Okay, so a quick recap, everybody. Let me erase my work first. You want to evaluate the integral, you have no choice but to go to the limit because we haven't discussed the FTC yet. When you use that, you are going to come up with the summation, simplify the summation, and then put it into the limit. To come up with that, the function is 1 minus x squared. A is 0, B is 2. So delta x is b minus a over n, which is 2 over n. So you find delta x. And x sub I is a plus I delta x to I over n. You put it in. You simplify this. When you get to this part, you notice you're dealing with two different summations. You separate them so you can deal with the summation of 1 as well as summation of I squared. When you put them together, this becomes 2. This one, it is only the first term that matters because the denominator is of degree 3 and the numerator is also of degree 3 and the rest of them have a smaller limit. Since you smaller exponents, because you're dealing with the limit, the rest of them will go to 0. Given f of x equals x cubed minus 6x, evaluate the Riemann sum taking the sample points to be right endpoints. A is 0, B is 3, n equals 6. Well, first of all, you can quickly graph this or even use a graphing calculator and understand we want to go from a equal to 0 to b equals 3. So 0, 1, 2, 3. So we mean this. And in other words, we want the following. We want this now. So what we are looking at here is to find the width with the function x cubed minus 6x and a equals 0, b equals 3. We get delta x is b minus a over n, 3 minus 0 over 6. So we get the delta x, which is b minus 0 over 6, which is 1/2. Now, from 0 to 3, we put a line segment here, everybody, 0 to 3, and we cut it into 6 equal parts, and each part is 1/2. This will help us with the calculation. Understand, we made 0 to 3. Let me just write the numbers here. So this is 1, 2, 3. We made it larger here, okay? So we start with the first point, a is 0, and then we add 0.5 or 1/2, and so on. Now, since we want to evaluate this using the right endpoints, that means, for example, the first one, okay, if you cut it in this format, the right endpoints, let me use this color, would be this point Let me just erase my work first. So this would be the first point, which means this area. And of course, uh, the way it works, below the x-axis becomes negative, above the x-axis becomes positive, and it's the difference of the areas that we are calculating. For the second one, let me use a different color. This is the endpoints, and this is the rectangle. All of these rectangles have delta x as the width, which is 1/2. They have different heights. This would be the height for the next one, the height for the next one, the height for the next one, the height for the last one. So because we are using the right endpoints, everybody, we use every point here except the first one. If we use the left endpoints, we don't use B. In this case, we don't use A. So therefore, R sub 6 in essence is delta x, which is 1/2, times f of 0.5 plus f of 1 plus f of 1.5 all the way to f of 3. So as an example, what is f of 0.5? 0.5 cubed minus 6 times 0.5. What about 1? 1 cubed minus 6 times 1. 1.5, 1.5 cubed minus 6 times 1. And 6 times 1.5. That's it. And I hope you see it's just tedious. It's not a big deal. It's elementary algebra. You add them up, you multiply by 1/2, and you get the answer negative 3.9375. So this is an approximation clearly, and again, let me erase my work so it becomes easier to see. Clearly, it's adding this 4 and subtracting this 2 because these 4 seem to have a larger area becomes negative. And it doesn't represent there, it's an approximation, okay? So this value represents the difference of areas. I can't emphasize this enough. So let's actually evaluate this. And to do so, we are going to go with the limit. Therefore, the function is x cubed minus 6x. A is 0, B is 3. And let's just write that first. Again, we want this area, the area that was mentioned, everybody. It's the same area. So we want this area precisely now. This time, we're going to go with the precise answer. And we calculate the delta x as b minus a over n, 3 over n. We calculate x of I as a, 0 plus I, delta x. So that becomes 3i over n. And now we are going to say this is the limit of this, f of x of I, delta x. We are going to calculate this one and then apply the limit. So we're going to work on this part, everybody. We're not going to write the limit. So we're going to work on this part and simplify it. So what is f of x of I delta x? Well, you have x cubed. So 3i over n cubed. You have minus 6x. So minus 6 times 3i over n. And delta x is 3 over n. So that's pretty simple. Three I over n cubed minus 6 times 3i over n times 3 over n. So let's distribute the 3 over n. And to do so, this is 3 cubed 27 over n cubed I. This is minus 18 over ni. And then we're going to distribute the 3 over n, everybody. So what do we get when we multiply this by 3 over n? This will give us AD1. This will give us n to the power of 4. I can take it out there. Understand there are two summations. So one of them is AD1 over n to the power of 4 summation of I cubed. The second one minus, multiply these two numbers is 54. These two is n squared. So minus 54 over n squared, and the I remains in the summation. So pretty straightforward, I hope. Now let's replace the I cubed with n squared times n plus 1 quantity squared over 4, and replace the I with n times n plus 1 over 2. So we're going to keep this number, and we do what I just mentioned. And first thing first, we notice this one has denominator 4n to the power of 4. This has exponent to denominator 2n squared. So because the degree for this one is 4, and if you look at the numerator, this one is n squared plus 2n plus 1. And when we multiply these two, we get n to the power of 4. So AD1, n to the power of 4, the rest is not important, over 4n to the power of 4, minus 54, n times n is n squared. And again, the rest is not important, minus 54 n squared, the denominator is 2n squared. Why is it that the rest is not important? You're dealing with a fraction, a rational expression, and you want to take the limit. So if I put that into a limit, everybody, in other words, this integral of 0 to 3x cubed minus 6x dx is equal to this limit. The limit as n goes to infinity of this expression. Now, since the degree is 4 for the top and the bottom, this becomes 81 over 4. Remember, we divide by highest degree term in the denominator, which is n to the power of 4. And this one, the same thing. We divide by n squared minus 54 halves. The reason I didn't write the rest, because even if you calculate, it doesn't change anything. So this is 81 over 4. This is minus 54 halves. I'm going to change it to minus 108 over 4. 81 minus 108 is minus 27 over 4 is the final answer. Okay. Evaluating integrals using signed areas. Use the signed area interpretation of the definite integral to compute the integral of negative 1 to 2x dx. So first and foremost, what is the function? F of x equals x. What are the limits? Negative 1 and 2. So that is the first thing we should notice. Secondly, we know how to graph this. This is a line through the origin. And we want to cover it from negative 1 to 2. Because this represents difference of areas, you calculate the area for this guy, you calculate the area for this guy, and their difference is the answer. Because both of them are a triangular shape, we use A equals 1/2 base times the height. As you can see, this point has coordinates 2, comma 2, so this distance is 2, and so is this one. So half of 2 times 2 is 2. So that would be the area for the green triangle. For the red one, This point has coordinates -1, -1, which makes this distance and this distance, both of them 1. So the red one is half of 1 times 1 or 1/2. And because this represents difference of areas, the answer is 2 minus 1/2 or 3/2. Now later on, we are going to use one of these fundamental theorem of calculus that indicates the integral of a to b f of x dx. This is a definite integral and it's a number. You find one antiderivative of that and evaluate it at the upper limit minus the lower limit. So capital F of b minus capital F of a. So with that being the case, this one is half of x squared. We're going to evaluate it from -1 to 2. And the reason I'm not going to put a constant here because it makes no difference, everybody. Why? Because you evaluate it with 2, you evaluate it with -1, you subtract them from one another, and then the constant will go. So if I put 2 here, I get 4. If I put -1 here, I get 1. So half of 4 minus 1. Again, 2 squared is 4, -1 squared is 1. So 4 minus 1 is 3. So it's the same 3/2 that we found here. The difference is sometimes this signed areas will fail because it may not be a geometric shape we are familiar with. This will always work. Having said that, I want you to try this later on. A graph and use signed areas to show that the integral of -4 to 1/6 x dx is -45. I'm giving you the question, I'm giving you the answer. I want you to go through the process that we did here and verify the answer. Here's another example. We want to use the geometry, the integral of -3 to 3 square root of 9 minus x squared, x squared. And of course, the function is this square root of 9 minus x squared over the interval of -3 to 3. So first of all, you can't integrate this. We will look at this in calculus 2, okay? So it can't be done with the techniques of calculus 1. You can't. So what do? We use the following concept. Reminding everyone that if you have a circle centered at 0, 0, x squared plus y squared equals r squared. If it's centered at h and k, x minus h quantity squared plus y minus k quantity squared equals r squared. So, and we know the area is pi r squared and the circumference is 2 pi r. So if this is the function g of x over y, I hope you see that I can square both sides. If I square both sides, I get y squared equals 9 minus x squared. And if I move this minus x squared, I get this one. So this is a circle centered at 0, 0 with the radius 3. However, again, let me erase my word. This is not a circle. This is a semicircle. As you may recall, when you have a circle, the top half is a positive and the bottom half is negative square root of 9 minus x squared. When you have a circle, so that would be, so here's the top half with this one, and here's the bottom half. It's represented with y equals minus square root of 9 minus x squared. I hope everybody remembers that. I'm going to erase my work again because I want to remind you the one on the right, you solve for x, you get x equals square root of 9 minus y squared. And the one on the left is minus that. In other words, this portion is this, okay? And this is the right side. So the top and the bottom have equations that are different. One is positive, one is negative. The right and left also the same thing. One is positive, one is negative. So in essence, we are dealing with a semicircle, okay, with radius 3. Therefore, you calculate the area of a circle and you multiply it by 1/2. So if the area is a pi r squared, that means pi times 3 squared. In this case, would be half of that. Half of pi times 3 squared, which is 9 pi over 2. And I can't emphasize this enough, everybody. Okay. So again, what is the point here is we are using geometry when possible. And of course, if the shape is not something we are familiar with, the geometry fails, you have to go with the fundamental theorem of calculus. Now, properties of definite integrals. Remember, definite integrals is a number. Let f and g be continuous functions over the interval of a to b. Definite integral at a point, the integral of a to a f of x dx is 0 because it doesn't cover any area. Okay, a to a. Or delta x is a minus a over 0, which is 0. The sum and difference rules, the integral of a to b f of x plus minus g of x dx is the integral of a to b f of x dx plus minus the integral of a to b g of x dx. So just should do them term by term. In other words, if this represents the area under the curve f of x, this is under the curve g of x, you just add them up. Add the blue one and the yellow one to get to the green one. That's the concept. Scalar rule, constant multiple, the integral of a to b c f of x dx is c, the integral of a to b f of x dx. In other words, if this is the function f of x, if you multiply it by a number 2, for example, it doubles up. Dominance, if f of x is larger than or equal to g of x from x equals a to b, then the integral of a to b f of x dx is larger than or equal to the integral of a to b g of x dx. We are just interested from a to b. So from a to b, g is less than f. So the area under the function f of x, obviously, versus g of x, the area under the g of x is also smaller. Bounding, max or mean. If m is less than or equal to f of x less than or equal to capital M from x equals a to x equals b, m lowercase m represents the minimum of the function, capital M represents the maximum value of the function. Then m times b minus a is less than or equal to the integral of a to b f of x dx, capital M times b minus a. And here's the reason. If you look at this function y equals f of x, and you see the area under that, if you continue and make this blue, that would be the area under the curve. Now, the minimum value of the function is here. If you draw a line, this is the rectangle with the width b minus a and times the height, which is the minimum value of the function. On the other hand, this is the maximum value. If you draw a line parallel to the x-axis, this rectangular shape, the width is b minus a, the height is the maximum. So that's why. Splitting additivity says if we have the integral of a to c f of x dx, we can split it in the following manner. The integral of a to b f of x dx plus the integral of b to c f of x dx. Notice b and b are the same, okay? And a to c, notice a to c. In other words, you look at the integral from a to b and then b to c, you can put them together in one shot from a to c. That's the idea of one shot, a to c. Opposite rule, the integral of a to b f of x dx is minus the integral of b to a f of x dx because delta x, which is b minus a over n, becomes the opposite. Constant rule, the integral of a to b c dx, just you multiply it by c. So c times the upper limit minus the lower limit again. It's just the concept of a rectangular shape. If f of x is larger than or equal to 0 from x equals a to x equals b, then the integral must be positive, and it becomes the area under the curve when the function is positive. Now, Given the integral of 1 to 3 f of x dx equals 6, 3 to 7 f of x dx is 9, the integral of 1 to 3 g of x dx equals minus 4. We're going to evaluate the following. We start with the integral of 1 to 3, 3 times f of x. Obviously, we can take the 3 out. This is identical to that, so 3 times 6 is 80. The integral of 1 to 3, 2 times f of x minus 4 times g of x dx. We are going to split that into two integrals, and we take the 2 and negative 4 out for each case. So the first one becomes 2, the integral of 1 to 3 f of x dx, and the second one becomes minus 4, the integral of 1 to 3 g of x dx. This one is replaced with 6, and this one with negative 4. So 2 times 6 minus 4 times minus 4. This is obviously 16. Let me just write both of them. So 12 plus 16 is 28. The integral of 1 to 7 f of x dx. Well, we can go with 1 to 3 and then 3 to 7. 1 to 3, 3 to 7. 1 to 3 is 6, 3 to 7 is 9. They add up to 50. The integral of 3 to 1 f of x dx, we have the integral of 1 to 3. So 3 to 1 must be the opposite of that. So minus the integral of 1 to 3 f of x dx, which is minus number 6. And now it brings us to section 5.3, the FTC, Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. It gives the precise inverse relationship between the derivative and the integral. The derivative of the integral of a to x f of t dt equals f of x. I want to make sure everybody understands what's happening. It says if you integrate and then you differentiate it with respect to the upper variable here, you undo everything and you get this function back evaluated at this upper variable. It's important to know that this variable now goes in there. Also, it's important to know these two must be the same. Okay. In other words, you can say f of m dm. The lower limit is a. A is some number, any number, 1, 5, 10, negative 18, makes no difference. The upper limit is x, that's the answer. So there are a couple of fundamental theorem of calculus. So the fundamental theorem of calculus, suppose f is continuous in the closed interval of a to b. If g of x is the integral of a to x f of t dt, then g prime is f of x. That's exactly what we are saying here. Okay. And then the integral of a to b f of x dx, this is a definite integral. This is a number, capital F of b minus capital F of a, where capital F prime is f. Just pick any antiderivative, capital F, and evaluate it, as I looked at the example we did regarding the signed area. So that's one way to write it. The other one is that just rewrite this two. And by the way, sometimes they call this one, they call this two, or vice versa. It doesn't matter. There are two FTCs. So let's start with one of them. We want to evaluate the integral of 0 to 1 x to the power of 7 dx. And again, one way is to go through the limit, which is very tedious. And now that we have FTC, it makes it very simple. So you to integrate this one is 1 over 8 x to the power of 8. Normally, we have a plus constant. We're not going to put it. It makes no difference. Here's the reason I'm going to explain again one more time. But for now, 1 over 8 x to the power of 8. This means evaluated from a to b, from 0 to 1. So first you plug in 1, then you plug in 0. So you get 1 over 8. 1 to the power of 8 is 1, minus 0 to the power of 8 is 0. So you get 1 over 8. Now, it makes no difference if you put a constant or not. Tip: even if we use another antiderivative, capital F of x plus c, in the evaluation theorem, the result will be the same, capital F of b plus c minus capital F of a plus c. Those c's cancel each other. We get capital F of b minus capital of a. That's why we don't bother to write that. All right. The integral of 1 to 2x to the power of minus 1 dx. I want you to notice whether we write 1 over x or x to the power of minus 1 makes no difference. So therefore, the answer is a natural log. And we do not write the constant because we are evaluating from 1 to 2. So that means you plug in 2, you plug in 1, and you get ln2 minus ln1. As you know, ln1 is 0, so you get ln2, and you keep it as ln2 because that's an exact answer. Now, I'm repeating the same question with different limits, and I'll tell you why in a moment. First, I'm going to write ln of absolute value of x from -2 to -1. And now I'm going to plug in. Notice what I did here. I didn't use the absolute value because both limits were positive. Fine. But now, if you don't use the absolute value, becomes ln of -1, which is undefined, so it's ln of -2. So you must use the absolute value because the limits are negative. And therefore, this is ln1 minus ln2. ln1 is 0. The precise answer is minus ln2. The integral of 0 to pi sine x dx. As you know, the derivative of sine is cosine, but the integral of sine is negative cosine. Negative cosine. So negative cosine x from 0 to pi. So we're going to plug in pi, plug in 0. So I'm going to keep the negative outside, and I'm going to write minus cosine of pi minus cosine of 0. Cosine of pi, -1, minus cosine of 0, +1. These two will give us -2. This negative makes it positive. The integral of a to power 2, 1 plus cosine t dt. We have done this without the limits. So as you recall, this is dt, therefore the antiderivative of 1 is t, and cosine is sine. As you know, the derivative of sine is negative cosine, but the antiderivative is positive. So you're going to evaluate it from 0 to power 2, which means you're going to plug in pi over 2 minus, you're going to plug in 0. When you plug in 0, obviously everything goes to 0 because sine of 0 is 0, and so is 0. So this is pi over 2, this is 1, and I'm going to keep it as such because it's an exact answer, everybody. The integral of 1 to 4, 5x squared of x plus 3 squared of x dx. And to find the antiderivative, we are going to do exactly what we did in the case of differentiation. We're going to change this to x to the power of 1/2. And this has exponent 1, 1 and 1/2. This is 5, x to the power of 3/2 plus 3x to the power of 1/2. And now we are ready to use the power rule in each case. So for the first case, 5 divided by 3/2 plus 1x to the power of 3/2 plus 1. For the second case, 3 over 1/2 plus 1x to the power of 1/2 plus 1. We don't have a constant because we are evaluating from 1 to 4, everybody. Okay. Now, what is 3/2 plus 1, 5 halves. So this is 2. What is 1 half plus 1? 3 halves. This is also 2. And so we are going to plug in 4, evaluate it, minus, we're going to plug in 1 and evaluate it. As far as 1 is concerned, 1 to any power is 1. So let's look at 4 to the power of 5 halves, which means square root of 4, which means 2 to the power of 5, which means 32, and times 2 is 64. 4 to the power of 3 halves means square root of 4, which is 2 cubed, which means 8, which means times 2 plus 16. I hope you see that this is 1, this is 1. So we are looking at minus 2 and 2/4. And that ends up being 76. Very straightforward, everybody. All right, in this case, let's evaluate the integral where f of x is defined as 2 when x is between -2 and 0, and 4 minus x squared when x is between 0 and 2. Therefore, we need to evaluate this integral in 2 parts in the following manner. The integral of -2 to 0, we use this is a piecewise defined function, this piece of the function 2, and from 0 to 2, we use this piece of the function 4 minus x squared. In this case, we get 2x from -2 to 0. In this case, we get 4x minus 1/3 x cubed from 0 to 2. By the way, just in case, even if it's from -infinity to 0 here, or 0 to infinity, we would be able to handle that, okay, as far as the evaluation is concerned. In any event, so 2x minus 2 to 0, 4x plus 1/3 x cubed from 0 to 2. So this one, we plug in 0, then minus 2. This one, we plug in 2, then 0. And we evaluate each piece. So obviously, this is 0 and this is 4. Then we have 8, and we have 8 here. In other words, minus 8 there. This is 0, this is 0. So what we are looking at, let me write here. So we have a 4 plus 8 minus 8/3. That's the idea. Or 12 minus 8/3. 12 is 36/3 minus 8/3 is 28/3. And so it's fairly easy to evaluate. Okay, so that's elementary algebra. I hope everybody's okay with that. Find the derivative of the function where g of x is given as the integral of 0 to x square root of 1 plus t squared dt. And I want to remind you that we are going to use the fundamental theorem of calculus, where the function given f of t is 1 plus t squared. So f of t equals the square root of 1 plus t squared is a continuous function. Why is that? I want to quickly remind you the reason. As you recall, if y equals square root of x, the domain is x plus is larger than or equal to 0. So in this case, 1 plus t squared is larger than or equal to 0. And I hope you realize that because of 1 plus t squared, worst case scenario, this is 1. So it's always the case, regardless of your choice of t. So it's continuous. When we say continuous, we really, and we don't mention the domain, we mean in all real numbers. So by the FTC, okay, the derivative is simply this, replace the t with x. G prime is the square root of 1 plus x squared. Again, notice the lower limit is a number. The upper limit is x. Just replace it. Okay. Let me erase my work, actually. Now, we have a similar situation we want to differentiate. The difference is not the lower limit. The lower limit is a number. It doesn't make any difference. But the upper limit here is x. Here is a function of x. Okay. And in that case, of course, sine t is f of t. We use the following. d dx of a to g of x, the integral of a to g of x f of t dt. Instead of t over here, class, we put x. Over here, of course, we have to put g of x. But by the chain rule, we need g prime of x. And I'm going to, in fact, show you working on this one two ways. Number one, just what I mentioned. I'm going to replace the t with the upper limit, whatever it is, which is x squared. So I get sine of x squared. And then times its derivative. The derivative of x squared is 2x. And I'm going to put the 2x in front and I'm done. But what I want to do, I want to show you the second method, why actually this works. Perhaps the second method is helpful. And I'm going to go with the integral of a to b f of x dx is capital F of b minus f of a. So I'm going to just work on this. Never mind the differentiation. In other words, let's evaluate this part, everybody. Let's evaluate this part and take the integral of sine, which becomes minus cosine of t from 1 to x squared. I'm going to keep the negative sign out, so I get cosine of x squared minus cosine of 1. So that is this function. But d dx is now differentiated. So if I want to differentiate this, I'm going to differentiate this one. And to make it easier, I'm going to say minus cosine x squared plus cosine 1. Okay, that. Now I'm going to differentiate this piece. When you differentiate that, class, first and foremost, before even you move on, I want you to see that this is a constant, that the derivative goes to 0. Okay, it's a constant. Cosine of 1 is some number. So you're working on this one. The derivative of cosine is negative sign. So minus makes it positive sine of x squared times its derivative, which is 2x. And that's exactly what we had here. Okay. I hope it's clear to everybody. A quick recap. You want to differentiate this using the fundamental theorem of calculus. F of t is square root of 1 plus t squared. Just replace the t with x, and because it's a continuous function, you're done. In this case, the upper limit is not x, it's a function of x. Your function is sine t, so you're going to replace the t with the upper limit, and then the chain rule says you have to multiply by its derivative. That's what we have here. We're going to take the derivative of the integral of 1 to x squared plus x tan t dt. And this is basically the FTC, okay? This one, the derivative of some number a to g of x, f of t dt. You're going to replace the t with the upper limit. So first notice that the function f of t is tan of t. And now replace the t with g of x, and this is your g of x, everybody. And so based on this, f of g of x, that means tan of x squared plus x. And then g prime, the derivative is 2x plus 1. Tan of x squared plus x times 2x plus 1. And of course, we move the 2x plus 1 in front, and we are done. Now, what about this case? Now, the lower limit and the upper limit, none of them is a number. How do you deal with that? Then the derivative of the integral of g of x to h of x f of t dt is you plug in h of x, the upper limit, f of h of x, and then times h prime. This is by the chain rule. The bottom one minus f of g of x and then times g prime. And again, this can be proved even if we go through this capital F of b minus f of a. And so with that being the case, notice the function f of t is t squared. So replace the t with sine. Okay. So you get sine squared x and then times the derivative of sine, which is cosine x. Okay. And then replace the t with tan x. You get minus tan squared and then times the derivative of tangent, which is secant squared. And there's nothing else we can do to simplify it further. What happens when the lower limit is a function and the upper limit is a number? Just interchange them. Put this up, put this down, and negate that. Okay? The function, of course, is square root of 1 plus t squared, and you just negate that. So now replace the t with the upper limit sign. You get minus, don't forget the negative, square root of 1 plus sine squared x. And then by the chain rule, you need the derivative of sine x, which is cosine x. I'm looking at this one. And so it's a good practice to put it in front. The final answer would be minus cosine x squared of 1 plus sine squared x.